Hello, Assalamu alaikum. So previously we discussed about feature descriptors and such as scale invariant feature transform, shift, and histogram of oriented gradients. All. Now today we're going to talk about RANSAC, random sample consensus, which can be used as a parametric model to fit boundaries to the objects, like fitting lines or fitting boundaries. And also it can be used in conjunction to the feature descriptors for multiple applications such as image alignment, image stitching, and so forth, which we are going to explore in this lecture. So let's start the lecture. So as I already told you, it can be used as a fitting model for parametric shapes such as circles, such as lines. So what we are going to do is we have to choose parametric model to represent a set of features whose membership criterion is yet not local. So we can tell whether a point belongs to a given model just by looking at that point. So the three main questions which arise here is what model represents this set of features best. We want to look for that particular model. We want to just look for features which it's like going through several model instances which gets those features, and how many model instances are there. So these are the primarily three questions which we have to find the solution for. And also the computational complexity is very important because it is infeasible to examine every possible set of parameters and every possible combination of features, which we actually did in Huff transform, because Huff transform method is very slow and it has a high computational complexity, as we discussed in our earlier classes. So we have to look for a model which performs these which comes up with a model which represents the feature best with minimal time complexity and minimal space complexity. So the example is line fitting. Is why we fit lines. We have already discussed that in our Huff transform lecture. So there are many objects which can be characterized by just fitting the straight lines like this. So we can just model their shapes by just looking at their lines. But the main question will the students will ask will be, wait, why aren't we done just by running edge detection? We can examine the shape, or we can just model the shape by just performing the edge detection techniques. But that's not the case. The line fitting is a different problem than edge detection. So there will be extra edge points, there will be clutters, and there will be multiple models to look after. So which points to go with and which line to go with are certain questions which cannot be answered by simple edge detection techniques. Also, only some parts of each line detected and some parts are missing. So we already discussed about hysteresis thresholding in the Kenny edge detector module. But the thing is that there were some missing edges as well, and we have to look for weak edges and strong edges. Now here, similar to that point, there are some parts of the lines which are missing, and we have to find a line that bridges that particular missing evidence. And there is also one thing which we need to take into account is the noise. So noise in measured edge points like orientations, we do not know yet at how to detect true underlying parameters. So what we do is, as we discussed in Huff transform, is we perform the voting. But it's not feasible to check all combinations of features by fitting a model to each possible subset. And also, voting is a general technique where we let the features vote for all models that are compatible with it. For instance, if we recall the Huff transform, what we used is we used an accumulator where we performed the voting function, and we marked a particular line at which the accumulator space would have maximum votes. So in this case, we have to cycle through features and cast votes for model parameters. and look for model parameters that receive a lot of votes, and that's exactly the same what we did in Huff transform. So noise and clutter features will cast votes too, but typically their votes should be inconsistent with the majority of good features. And it's okay if some features are not observed, as model can span multiple fragments. But in this case, it's like if I tell you a particular analogy between the RANSAC and the Huff transform is a kind of an analytical solution. A sort of, because it's a kind of a complete solution where you will find the lines for sure. But if you use RANSAC is a kind of a numerical solution to that, where you assume some part of the information, you take into account that particular information, and you try to fit the model with actually minimal number of requirements. So in that case, outliers actually are the biggest threat to this particular method, because loosely speaking, outliers are points that don't fit the model, and if we take into consideration the outliers for fitting, that will be a disaster. So in this case, you can see that if we fit the inliers, we would get the maximum response, but by fitting the outliers while performing the least square estimation, we can get a skewed result. So you can see here that the line which is fitting, it's not related to, or it's not corresponding to the inliers which we visualize here. So that's the problem. We want to get this kind of result while we are getting this kind of result. So the solution is to develop a method, or to estimate a method which is robust to outliers. But the outliers aren't the only problem here. There are some multiple structures which can also skew the results, and the fit procedure implicitly assumes there is only one instance of the model in the data, like this example. So we are only modeling one instance at this point, not the multiple instances. So there is a method which was proposed by Fisher and Balls in 1981, that is random sample consensus. And the approach is to avoid the impact of outliers, so that we should only focus on the inliers and use them to particular fit the model. So the intuition is, if an outlier is chosen to compute the current fit, then the resulting line won't have much support from rest of the points. So it's also based on voting. So how we run the loop for RANSAC? We randomly select a group of points on which to base transformation estimate, like group of matches. We compute the transformations from that seed group. We find inliers to this transformation. If the numbers of the inliers is sufficiently large, we recompute the least squares estimate of transformations on all of the inliers, and we keep the transformation with the largest number of inliers. So let's just take these points with respect to a particular line fitting example, which we will go through in the next couple of slides. So let's say we have these kind of points. Now what was the first point was to randomly select a seed group of points on which to base transformation estimate. So we randomly select these 2 points. That's the first step. The second step is to compute the transformation from seed group. We compute the transformation, which is represented by this line, and then we find the inliers to this transformation. So these are the inliers in this transformation. Now what we have to do is we have to recompute least squares estimate for transformation on all of the inliers and see that which transformation gives us the largest number of inliers, so we should keep that transformation. So again, we take a different set of seed group, we compute the transformation, and then we compute the inliers. So it is better than previous one, which has 4 counts, but still we have to rerun the experiment. Now let's see, we compute this transformation, we take this pair of points, and then we compute the transformation, and then we compute the inliers. So now it's 19. So it means that the result is better than the previous two transformations. Now let us consider another set of points and let us compute the transformation and count the inliers. Now the inliers is 13. Now in this case, what we can do is we can like compare different transformations with respect to different seed points, and then we have to consider, or we have to store the transformation having the largest amount of inliers. So we will keep this count equals to 19 transformation, which is highlighted in this black color right now. So another example is, I'll go through this example like quickly. So we have already discussed this. We will randomly select subsets of 2 points, in this case this, and then we compute the transformation, and then we compute the distances. So to like determine that what are the number of inliers in this case, and the inliers is 3. Similarly, we take these points, inliers is 3. We take these points, inliers is 15. So we keep this transformation which has the highest number of inliers. Now RANSAC, this is a particular snippet of the RANSAC algorithm, which is also mentioned in the book of Forsyth and Pence. So what we have to do is we have to determine these parameters, which is the n, the smallest number of points required, k, the number of iterations required, t, the threshold used to identify a point that fits well, and d is the number of nearby points required. So we have to perform this RANSAC algorithm for k iterations, which we have already determined here. We have to draw a sample of n points from the data uniformly and at random. We will discuss about this, that how to select these points, fit to that set of n points, and for each data point outside the sample we have to test the distance from the point to the line against the threshold t. If the distance from the point to the line is less than t, the point is closed and we consider them inliers. If there are d or more points close to the line, then there is a good fit. Refit the line using all those points. So basically d is the number of nearby points which we have already determined here, and then we use the best fit from this collection using the fitting error as a criterion. So let's see, let's discuss this in simple words. So this algorithm tells us that we have to randomly select a sample of s data points to initiate the model. We have to determine the set of data points which are within a distance threshold t of the model, as we can see here. So we compute the distances using the thresholds. This is basically the threshold which determines that which point should be considered as inliers and which points should be considered as outliers. So if the size of number of inliers is greater than some threshold t, we have to re-estimate the model using all the points in consensus set, and after n trials the largest consensus set is selected and the model is re-estimated using all those points. So basically this algorithm was proposed by Fisher and Balls in 1981, and if you want to have a look, or if you want to have a detailed look on this algorithm, just read this paper, A Paradigm for Model Fitting with Applications to Image Analysis and Automatic Cartography. So let's see that how we can do this. So this is the formula which we have to like compute, or which we have to consider for solving the n, which is the number of samples that we need to compute. Now the question will be, where in the world did that come from? How did we come up with this particular equation? So let's dissect that, what this equation actually means, or what the fragments of this equation actually mean. So here, this particular E is the probability that a point is an outlier. We assume that we know E, and the probability that a point is an outlier is E, so we can assume that 1 minus E would be the probability that any point is an inlier. So it's like a set theory. If you remember the set theory, that if it is a universal set and you want to find that what is the kind of intersection between the two sets, you actually kind of take a difference of it. Or if you have let's say, let me give you an example. So if you have this universal set and if you have this A set, so if we want to know that what is here, what you will do is you will do this universal minus subtract or universal intersection A. So we want to know that not intersection, it's let me erase that. So it's basically subtraction. So that's the same thing which we are going to do. So as we know that the maximum probability is 1, so if E is the probability that a point is an outlier, we can subtract it from 1 to find the probability for being a point as an inlier. Okay, so let's move. Now we have known that what is 1 minus E. So let's see what is 1 minus E to S. So S is basically number of points in a sample, and this equation shows that the probability that a sample of size S is all inliers is 1 minus E to power S. So it's like 1 minus E shows that the probability of being an inlier, and the S shows that that is the particular sample of size which are all inliers. So this is the representation of that. Now remember the previous example I discussed in the previous slide, that if we want to know that what is the difference from the universal set, like the complete probability, so what we do is we just subtract it from 1. So we would do the same thing, we subtract it from 1 to know the probability of getting at least one outlier in this sample. So remember that 1 minus E to S is the probability to get all the sample is like the points in the sample set, all the sample set are inliers. That's the probability we computed previously, and 1 minus is to compute the probability of getting at least one outlier in that sample. And then if we just add n to it, so it says that with n samples, it's like trials, the probability that all samples have at least one outlier is this formula, 1 minus E to S to n. So what we are looking for is we are looking for at least one outlier in that whole particular sample. And then if we just add 1 minus to it, it means that we want to find at least one sample to have no outliers. So the probability of having not outliers is 1 minus B all outliers. So we'll pick the probability of not all outliers to be some high value like 0.99 to get to compute this particular formula. So how can we just derive the value of n which we want to compute from this particular formula? We can perform these simple steps. So remember that this one will go here. Let me just write it. So this one will go here, so it becomes minus 1 minus 1 minus E to power S to power n equals to P minus 1. So there is minus, and if we just send the minus there, or if we just multiply with the subtraction sign on both sides, we get 1 minus E to S power n equals to 1 minus P. So that's basically is mentioned here, this thing. And if you take the log on both sides, you will get this equation. So if we know E, we can solve for n, where n is the number of trials needed to get at least one sample of all inliers with probability p of not all outliers. So this table is basically from Hartley and Sisserman, which was published in 2000, which states that the number n of samples required to ensure with a probability of 0.99 that at least one sample has no outliers for a given sample size S, this S, and a proportion of outliers E. So this table shows the proportion of outliers epsilon versus the sample size S. That this would be the little s. So if we had, let's say, 10% outliers here, if we say 10% outliers and we have to choose 8 points from the sample size to fit our model, we need at least 9 sample sets. We need at least 9 sample sets or 9 iterations in this case to be sure within 90 to 99% probability that we wouldn't have any outliers. But you can see though that if this goes up very large, if we have a large number of outliers, let's say 50%, we need to consider 1177 iterations to find a sample set of 8 points with 90 to 99% probability. So this particular method assumes that we should have less amount of outliers, but if the number of outliers goes up, it would take a lot of computational time. So let's see an example for this. So let's say we have a minimal sample size of S equals to 2. We assume that the proportion of the outliers is 2 here. So it would be 2 divided by 12. So this will be 1 divided by 6 and approximately 20%. So this is how this is calculated. So if we use the previous formula, which is this, n equals to log 1 minus p and log 1 minus 1 minus e to s, let's solve this here. So it's log 1 minus 0.99, that's the probability which we are looking for. Remember this p is 0.99 divided by the log of 1 minus, and sorry for my bad writing here because I am writing with mouse. So 1 minus 1 minus, this is 20%, so I can write it as 0.2, and the s value of s is 2, so this would be square. So remember, this is the same formula, 1 minus 1 minus e whole power s. So here e is 20%, so it will be 0.2 and s is equal to 2, so I can write it like this. So if you will solve it, you will get log of 0.01 divided by log of 1 minus, this will be 0.8 whole square, which will be log of 0.01 divided by log of 1 minus 0.64, which will be log of 0.01 divided by log of 0.36, and finally we will get the value of minus 2, which is log of 0.01, and the value of 0.36, log would be minus 0.4437. So this would be minus 0.4437, and we get the value of 0.4437 would be 4.51. So this would be 4.51 approximate. This would be equal to 4.51, and it will be approximately equal to 5, and that's what we get here. N equals to 5. That gives us a 99% chance of getting a pure inlier sample, compared to n equals to 66 by trying every pair of points with this case. Now in this case, if you will see that you have 20% of points, and here the proportion of outliers is 20%, and s equals to 2, and with respect to 0.99 probability we approximately get n equals to 5, and this is what we get. So it means that this formula works in this case. So what is the acceptable consensus set? So we have seen that we don't have to exhaustively sample subsets of points, we just need to randomly sample n subsets. However, typically we don't have to sample n sets. We can early terminate it if we find a particular set of data points, or if we just satisfy a particular condition to have a certain amount of inliers in our iterations. So we can terminate when inlier ratio reaches expected ratio of inliers, which can be determined by this formula, which is the probability of outlier proportion multiplied by total number of data points. So RANSAC divides data into inliers and outliers, as we have seen, and yields estimate computed from minimal set of inliers. So in this case, if you can see that we can improve the initial estimate with estimation of our own inliers over all inliers, for example with the standard least squares minimization. So if you are electronics student, and if you have studied numerical methods, which I have taught in my last semester, you would know that the least square estimates can be performed by linear regression. So the underlying computation is still the same as of linear regression. But if you are IT students, don't worry, we will not discuss the details regarding the linear regression in this lecture. So this may change inliers to alternate fitting with reclassification as inlier or outlier. Now what are the advantages of using RANSAC is that it is a general method suited for a wide range of model fitting parameters, model fitting problems, and it's easy to implement, it's easy to calculate its failure rate, and it's fast, as we have already discussed. But the disadvantage is it only handles a moderate percentage of outliers without cost blowing up. So we have already discussed from the table that if you have high or a kind of a large proportion of outliers, the method probably won't work. So many real problems have high rate of outliers, but sometimes selective choice of random subsets can help. A voting strategy like the Huff transform can handle high percentage of outliers, which we have already discussed in our previous lectures. Now the applications which can be used for this, the application which can use RANSAC is video stabilization. I will show you a demo for video stabilization in shortly. We can use it for image stitching, as we used SIP, which we discussed in our previous lectures. We can use it for image mosaicing, and we can use it for line fitting and more. So we'll discuss some of the applications here in our demos. So see, this is a kind of an example of what we say is kind of an example for RANSAC. So here you can see that you have two kind of images and you are trying to fit. So the red is basically the ones which are rejected by second nearest neighbor criterion. The blue ones are RANSAC outliers and the yellow ones are the inliers. So these points will be actually matched to stitch the both of these images in this case. So you can recall from here that we use normalized cross correlation to track interesting points from one image to another, as we did in this. Interesting, when I say interesting, I refer to high local variance. So we still had some incorrect matches even though correlation score was high. Identifying incorrect matches, like picking a subset of matches, fitting a matrix A in, as we did it with eigenvalues and eigenvectors, or if you have already a knowledge about fundamental metrics, but if you don't, just consider not knowing about it, it's okay. We may discuss fundamental metrics in our upcoming lectures, but if we do not get time, so we will not discuss it. But you can actually learn about fundamental matrices from internet. There is a lot of literature, or there are a lot of videos available which explain you about the fundamental metrics. So we can match, or we can just model these points to fundamental metrics and see how many other matches agree with this particular fundamental matrix. So those matches that agree with A or fundamental matrix are inliers, other matches are outliers. So we can do this kind of stuff to improve the matching process. So let's see. So if let's see an example here. So what we are doing is we are clearing all the variables right now. So this is a kind of a video file, and you will see the subsequent frames of this video file here. In this example, we will see that. So let's see the result for this section. So this is the frame A and this is the frame B. So you will see that it's a kind of a motion estimation, that a car is like moving, and it is like recording the video at the same time. So of course there would be some translation between the subsequent frames of the video, and this is you can see that this is a kind of a kind of a displaced frame with respect to this frame. Now if we show a pair of this, you will get a more realistic view. So basically the frame A is represented by red and frame B is represented by can. So you can see these kind of translations of car, of trees, of the backdrop sceneries, and this board. So this is a kind of a translation or the displacement from the reference frame. Now what we are doing here is we are detecting fast features, which are of course a type of a corner features, which we have already seen in our last demo. So we detect corner features from frame A and from frame B. So you would see that we can match this point to this point, we can match this point to this point, and similarly we can match these points to these points, and so forth. So now we want to extract features and we want to match those features from point like frame A to frame B using fast retina key points, freak descriptors, which can be used, or which are actually a kind of by default used in MATLAB. So if you will see, we have got this result. So this O feature key points are from frame A, and the key points which are represented by positive sign are from frame B, and you can see that how they are actually matching from one frame to another frame. Now what we can do is we can use RANSAC for estimating the geometric transformation. In MATLAB it is referred to as M estimator sample consensus. So we will use this estimate geometric transform, which refers to this M estimator sample consensus method. So we will use this method, and you can see that now the features, the key points which we extracted or which we matched are actually aligned. But in this case you will see this particular red frame, because as we are matching the key points, this will actually create a kind of a padding problem here. But it's okay, because the main problem is to align the video for all the time, for all the subsequent frames. So we can also extract and rotate we can extract the scaling and rotation part of the submatrix by using the IM warp here. So if we run this, you will see that we have actually aligned both the frames here with this zero padding thing. Now if you want to see it in on the go, just see it here. So I'll just take this out and okay, so this is how to show you this. So let's just so basically you can see this is so you can see this video. Let me run it for more. So you can see this video is going on, and it is actually aligning subsequent frames with respect to the RANSAC. Now let's see another demo of this. I have already mentioned the code in my slides, so let me show you the code here. So this is the code where you can actually align. So I'll just run the code step by step and let you know that how this works. So let's see, let's clear out all the variables. So this is the transformed image, and this is our base image. Now what we have to do is we have to align this with this image. So what we can do is we can again detect and extract the features. So now we will detect the surf features, speed up robust features. And we will match those features. Now you can see that we have matched the surf points and the outliers. Now we'll use this estimate geometric transform here, which is the RANSAC one. So what we get is we get only the inlier points. Once we get the n layer points, we recover the original image from the distorted image, which looks like this. So this is an example from MATLAB. I can also show you the examples from Python here. So let me show you an example of Python. I've already mentioned the code here with respect to Python, but now we will look a kind of implementation to it. So let's just similar to the previous demos, we have here Anaconda prompt, which we will use. Here we have the file name is block. So here you can see that we have some correct correspondences which have been which are represented as inliers, and the red ones are the outliers. So we can use RANSAC for finding the inliers and outliers respectively. So this is all for now, and I'll come up with another topic, which is the image segmentation. So I'll shortly upload the videos which will cover the topics of image segmentation, because there are many techniques to it. So I'll try to cover as many techniques as I can. So if you have any problems with respect to RANSAC or with respect to the things which we discussed in this lecture, please let me know in the comments or in Google Classroom. Thank you.